great. Yeah, again, my name is Matt Varner. I'm a fish biologist with the Bureau of Land Management, and I'm going to talk about fluvial geomorphology and regional curves. So let's see here. Let's get this thing moving. Maybe it's thinking. All right. So today you've heard a great deal about aquatic habitats, floodplains, and fluvial geomorphology. My presentation is just going to scratch the surface of fluvial landscapes and channel classification, and then wrap all that up with an introduction to regional curves. And again, thanks everybody for hanging in there. I was pretty impressed with the size of the group today and the fact that everybody seems to be holding strong still here even after lunch. So appreciate that, and hopefully you can gain something from this presentation. I know a lot of it's already been touched on. To start with, one of the basic questions obviously is, why is channel geomorphology relevant to fish passage? You just heard from Will Harmon, and in his presentation, you learned about several key elements of geomorphic function and the stream function pyramid framework, which is reflected here on the slide, at least the pyramid portion. In many ways, the ability of a culvert to facilitate fish passage is related to the ability of that structure to transport water in the channel and on the floodplain, as well as wood and sediment. That's really captured by that level 2, level 3 function in the pyramid. But when those functions are impaired by a structure like a culvert, fish passage is also impaired. The geomorphology of the watershed and the channel played really important roles when we think about infrastructure like culverts. Basic geomorphic principles help you understand the stream processes and then the difficulties that can arise as well when we place culverts across streams in various positions in the watershed or drainage. And those processes change with that location and along the reach where a culvert might be located or is planned. And so because channels are dynamic and they respond to changes in the watershed by adjusting either downstream or upstream or vice versa, depending on the channel's elevation, it's really important to really understand that geomorphic context when you're planning these types of projects. So with that, I think what I'm going to do is cover several key factors related to stream geomorphology, and Lane's balance, which was touched on earlier, at least mentioned, provides a really good visualization to consider about how all these different factors contribute to how that stream channel might respond to some kind of structure, whether it's a culvert or a bridge or what have you. There's a whole host of questions to consider when planning a fish passage project. We touched on the first question already with Will Harmon's presentation and the stream function pyramid. Other aspects, though, relate to understanding the fluvial landscape, the channel characteristics within your reach, and the evolutionary processes that might be present in that project reach or even adjacent to the reach. So for the next series of slides, I'm going to provide an intro to valley types, channel classification, and channel evolutionary sequences so that you can better reflect on these questions for your specific projects. All right, well, I know this is a busy diagram, and I apologize. But it is a really useful diagram to think about and consider when you're thinking about the fluvial landscape or the valley type that you're in. And this comes from a publication developed by Dave Rosgen, and I have all the references at the end on the last slide, so you don't have to worry about jotting anything down. So this comes from Rosgen 2006, and it's basically his valley type key. And there's a lot more that goes with it, obviously. Big picture, the valley type classification segregates valleys into 22 broad geologic categories that reflect their origin and represent the boundary conditions that influence channel morphology. This valley type key not only helps you characterize the landscape influencing your project reach, but it also provides insight into the stable channel types. And I'll talk a lot about channel types later, but those are reflected in bold. And then it also includes channel types that might be present in that valley type in an unstable state. And those are the channel types that are in brackets and not bolded. The first step in understanding your fluvial landscape is determining if a stream section is located in a confined or unconfined valley. Valley confinement describes the degree to which the bounding topographic features, so you can think about hill slopes, alluvial fans, glacial moraines, river terraces, those types of features that limit the lateral extent of the valley floor and floodplain along a river. a general rule of thumb is that if the valley width between those bounding features is less than 7 bankful stream widths, the valley is confined. And so if it's greater than that, it would be considered unconfined. So those are the two kind of initial breakpoints. The next step is determining your valley type by examining the geology and boundary conditions, or the stream bank floodplain material associated with that particular stream reach. Are you seeing material in the stream or surrounding floodplain that was transported over geologic time by the stream? In other words, is it alluvial material? Are you seeing material left behind by glacial activity? So those would be glacial valleys. And likewise, besides glacial and alluvial valleys, which are pretty common in Alaska, another common type in Alaska are colluvial valleys. And so that'd be material that's transported by gravity. Given that quick overview of valley types, I'm going to highlight a few examples with some photos and some additional material from the Rosgen River Field Stability Guide to help you kind of stitch some of this together, at least visually. The first one I want to mention is confined alluvial valley types with narrow floodplains. As I mentioned before, the classification process described in Rosgen also provides information about stable stream types. So for this valley type, we would expect to see a Rosgen B, C, or E channel type in a stable configuration, but you might also see A, B, F, and G channel types, which are in brackets here. And those would be kind of unstable conditions. And I'm going to dive a lot more into channel classification, so don't scramble around wondering like, what the heck am I talking about? We'll get into that a little bit later, but I at least wanted to raise some awareness as to some other benefits with valley type classification. This particular stream photographed here is a section of Wade Creek along the Taylor Highway. Here's an unconfined alluvial valley type with a terraced floodplain. This image here is Seattle Creek off the Denali Highway with my Labrador Retriever. This is another pretty common valley type in Alaska that you might encounter. This section's on Upper Thunderbird Creek just out of Chugiak, and it occurs in a confined alluvial inner gorge valley type setting. Confined V-shaped colluvial valleys are also common, like in mountain headwater type systems, like this one in the Brooks Range. Sure, this one, you look into headwater systems, these really confined V-shaped valleys, very common. Likewise, confined U-shaped valleys also are common in these mountain headwater systems, and this is an image of Franklin Creek in the 40 Mile. Confined glacial trough valleys are also common. And I think most people, when you think of glacial valleys, you think of these braid plains, glacial outwash plains, where you see these D channel types or braided channel types. So another thing to remember, though, is that you can also see single thread B and C channel types in a stable configuration in these types of valleys. This is an unnamed stream located in the Brooks Range. Lastly, I'll mention well, actually, I might have, no, this is the last one. Unconfined glacial trough valleys are also common in Alaska and easily recognized by the presence of the braided channel types, pretty common. This is the Matanuska River. Most folks, I think, have seen the Matanuska because the highway system here in South Central, but much like confined glacial valleys, this valley type can also support stable B and C channel types, which are single thread, although we most commonly associate kind of these braided forms with this type of glacial outwash plain setting. And there's a multitude of other valley types. These are just some of the ones. Sorry, if you remember, there's 22. So these are just a handful to think about. This figure it was shown in other presentations today. It provides a good general overview of the Rosgen channel classification system. Stream channel classification is frequently used as a watershed planning, management, or restoration tool. And it's important to note there are multiple ways to classify a stream reach. I'm focusing on the Rosgen channel classification system. It's one I'm most familiar with. This approach is form-based, and that means that it relies on direct channel measurements of physical attributes to put streams into bins or classes. Because of that, some people think about Rosgen in particular as a channel classification system that ignores stream processes. That's a common criticism, I think. But I think it's important likewise to remember that a basic tenet of geomorphology is that form implies process. Here we have a broad level look at the Rosgen system with major stream types shown at the bottom, ranging from a plus on the left to going to the right to a G. And that's based on slope, cross-section, and plan form characteristics. And so this is a simple overview. I want to dig now a little bit deeper into the specifics of the classification system. You also saw this image earlier today in at least one presentation. Here we see the 8 major morphological stream types and how they can be identified using 5 initial definitive criteria. And we start with channel pattern. Is it a multi-thread or is it a single thread channel? Then we move through those specific definitive criteria: entrenchment ratio, width to depth ratio, sinuosity, slope, and bed material. And that allows you to determine within your project reach what channel type or types might be present. As I mentioned before, the Rosgen classification system relies on direct channel measurements to classify a channel. And one important term that you've heard today and you'll continue to hear throughout this workshop is the term bank full. Identifying the geomorphic cues that relate to the bank full discharge can be challenging. Anybody that works with streams and has spent time identifying bank full will tell you that it can be difficult, and it can. I'm gonna focus in on what we commonly associate in the field with a bank full feature and the importance of using multiple lines of evidence to make your determination. Based on this diagram, you see that the elevation of bank full is the top of the stream bank or the incipient point where water leaves the channel and enters the floodplain. Depending on the stream type and the conditions of the stream reach, bank full may or may not be the top of the stream bank, but that's one of the most common indicators that we use. Also of note is that the feature often corresponds to a discharge event that happens statistically every 1.5 to 2 years. I'm going to go through now the details, the primary indicators with some photos to help you visualize where this feature occurs and how to identify it in the field. When assessing your project reach to determine bank full and take measurements of bank full, I walk the stream as much as possible, both inside and outside of your project reach. And I primarily focus on the straight riffle sections to look for bank full indicators, with one of the best indicators shown here as that first flat depositional feature or active bench adjacent to the stream. At this site, the first flat depositional feature is obvious. It's dominated by sedge species, and more as you move away from the stream on the back of that bench, you see a transition to willows. A related indicator is a break in slope between the active stream channel and the floodplain. The key here is thinking about what point does that channel fill up and begin to spill out on the floodplain. And so I often get down and feel with my hands, where is that break point? That is your bank full indicator, where that break point is. Particle size shifts are another pretty good indicator. Bank full elevation is often found above the location where particle size is changed from coarser bed material to finer particles deposited on the stream bank during these high flow events. In this case, a change in particle size coincided with that change in slope and the height of an active bench on the opposite side of the stream. Remember, it's this idea of multiple lines of evidence that you want to keep front and center as you do this. You want to look for a multitude of indicators and be assessing the elevation of those indicators using the water surface. And I'll show a snapshot of that here coming up. Point bars, which are depositional features in the active channel, can also help inform the location of bank full, but you need to be cautious with these and use them in concert with the other indicators. When looking at a point bar, for example, I pay attention to the highest elevation of that point bar feature in relationship to the other indicators that might be present within that reach. Vegetation community changes are also useful, but they can be misleading. The lowest elevation of cottonwood, birch, and alder are pretty good, but when you see species like dogwood and various species of willows, it's important to understand that they can occur above and below that bank full indicator or bank full elevation. So here we see woody species at the top of the bank and herbaceous species and moss present below bank full. down to the scour line where the stream is, where the water surface is. Those were the primary indicators. And if you have limited primary indicators, you can also look for secondary indicators, such as undercut banks and straight channel sections. The ceiling of an undercut is often associated with the scour line and is located below bankful. So you can find the scour line and that undercut and then look directly above that. In addition, bankful is typically at or above the highest stain line on rocks, which may coincide with the lowest limit of mosses or lichens as well. In this case, other indicators like particle size and vegetation changes coincided with an elevation just above the stain line noted here in the image. Bankful can be associated with the elevation of deposited drift debris as well. But again, this is another one you have to be careful with because debris captured on limbs during early breakup can rebound after all the ice and everything is gone. And if you use that, it'll make bankful appear higher than it actually is. In this case, debris caught in the vegetation closely aligned with the elevation of the active bench directly adjacent. So it was a good complementary indicator. Accumulations of unconsolidated material and the lack of deciduous leaves can be a secondary indicator of bankful as well. Here we had accumulated sand and a lack of leaf litter that coincided with the elevation of an active bench on the opposite stream bank. So it was a good complementary indicator again. I mentioned evaluating those indicators in their height above water surface. And so as you walk the reach looking for these indicators, keep in mind that that elevation for your indicator should be pretty consistent. You shouldn't have a bunch of variability. And the way I often look at it, and I think many folks look at it this way, is you take a couple tapes or a tape and a rod or a trekking pole, and you walk and you just check the elevation of those features within your riffle above water surface and see what measurements are consistently showing up. And so you can see in this image, you have a vertical pocket rod and then a horizontal tape, and there's a little bubble level on that tape. So you can level your line horizontally and then just look at that elevation above water surface and figure out what's that consistent elevation you're getting above water surface. And that'll help you hone in on what's the most consistent and bankful indicator within your reach. This next series of slides, I'm going to go through some actual field examples to just kind of help put this together. For streams with well-developed floodplains that are not in size, like what we see here, the bankful elevation is an obvious break point at the top of the stream bank. And so water comes up and it goes out onto the floodplain. It's a pretty easy call in a setting like this. Other streams, in other streams, like in this one where you have moderate to steep headwater type scenarios, it's important to understand that you're not going to have well-developed floodplains here, but you probably will have a small flood-prone bench adjacent to the channel. And so that small bench is your bankful. It's also important to not be confused by the formation of an inner berm feature. These are features that are below bankful, and they often are the boundary of the low flow channel. They can be dominated by moss. You can even have willow species within that inner berm. In this case, we have a scour line, and you can see this little inner berm feature. It's important to not let that mislead you. As you survey, you need to look at these features. And if you had a cross section here, you would want to capture that inner berm surface in your cross section, take photos of it, etc. But at the end of the day, your bankful is that break point where the channel fills up and water exits the channel. At the same time, it's also important to understand that some streams don't have a connection to their floodplain because they've incised, they've downcut due to some change in the watershed. And so your bankful stage may correlate to a small bench or even a scour line on the stream bank in an incised setting. In this case, the top of the bank is now has been abandoned. So your floodplain, your historic floodplain has been abandoned. And you would refer to that as a terrace, a low terrace. This stream has incised about 1.5 to 2 feet, so it's disconnected from its floodplain. The process is now, the channel process that it's going through is continuing to undercut that bank, allow it to slough, etc., widen, and eventually we'll see the formation of a new flood-prone bench at this site. But in its current configuration, you have a scour line, bankful within the channel, and your old floodplain terrace above. And this isn't uncommon. This site is one that I'm very familiar with. It's incised over 50 feet as a result of placer mining, which makes identifying bank full extremely difficult. In these instances, it's important to walk upstream and downstream of your project reach, especially if you have reference condition or largely unimpaired conditions upstream and downstream. And you can take those same measurements above water surface to that bank full feature and carry that into this impacted reach. As long as you don't have a junction of a large tributary, et cetera, you can do that. Other tools that you can use are regional hydraulic geometry curves or regional curves, and I'll discuss those towards the end of my session today. So hopefully now you have a kind of a basic understanding of bank full channel measurements, and we can jump back into Rosgen channel classification a bit. The first one, once you figure out your single thread or multi-thread, you're going to look at entrenchment ratio right here at the top, and that's one of the first delineative criteria to consider. And just simply, that's a field measurement of vertical containment, and we assess that as a ratio of the flood-prone area width to bank full width. The flood-prone area width that's shown here in the diagram, that's a width that's obtained at an elevation at 2 times the maximum bank full depth. And so you can see the channel to bank full, and then now we're going to go twice that deep, right? That lateral extent is your flood-prone width. So now that you have flood-prone depth at that height, you know your width, and how it relates to your bank full width, and that ratio is your entrenchment ratio. It's also worth mentioning that 2 times max bank full also loosely correlates to an area that would be inundated by a 50-year flood event. So that's kind of your 50-year floodplain. For entrenchment ratio, we just need to keep a couple numbers in mind, 1.4 and 2.2. If the entrenchment ratio is less than 1.4, the stream is classified as entrenched or vertically contained. And so you're going to focus on A, G, and F channel types. If the entrenchment ratio is between 1.4 and 2.2, then it's considered moderately entrenched, and you're just going to be looking in that B bucket. If it's greater than 2.2, then the stream's not entrenched, and you're looking at CE channel types or DDA channel types. Basically, a stream with a high entrenchment ratio means that it has a well-developed floodplain, whereas a low entrenchment ratio means it has a limited floodplain. So that's your first cut. The next thing that we look at is width to depth ratio. And that describes the channel shape, and it's derived from a field measurement of that bank full width divided by the mean bank full depth at a riffle. A large number in this case indicates a wide, shallow channel, while a small number indicates a narrow, deep channel. The key item here is that the break point for a single thread is 12. I also think it's important to note, and you'll see it at the bottom of this slide, it talks about a continuum of physical variables, and it allows that for entrenchment and sinuosity, you can vary your units by 0.2 plus or minus, and then for width to depth ratio, it can vary by plus or minus 2. So it could be anywhere from 10 to 14, for example, instead of just thinking about it as 12. But that allows for just acknowledgement that there's situations where channels are transitioning. There's a continuum. These aren't fixed. Oftentimes you will find channel types that aren't cookie cutter and fit into these bins. There is some flexibility built into this classification. The next thing we want to look at is sinuosity, and that's the measure of a stream's crookedness. Most folks are probably familiar with that term. Specifically, it's channel length divided by the straight line valley length. The greater the number, the higher the sinuosity. Things to note here is that sinuosity is closely related to slope. So natural streams with steep slopes have low sinuosities. As you think of, they're pretty straight, right? Streams with low slopes typically have higher sinuosity. So you can think when you're flying in Alaska and you look down at the ground, you often see on the valley floor these really tortuous type stream systems, high sinuosity. Those are in low gradient valley bottoms. Let's just do a quick look here. This is the computations. If you're curious, you have your stream length. You can see the meander pattern in this particular stream, and then the straight line valley length gives you a sinuosity of approximately 1.4. Heather's going to dive into this top sinuosity quite a bit deeper when she gives her survey presentation later on in the workshop. So at this point, hopefully, if you're still awake, you have a pretty good understanding of these broad channel types located within potentially your project reach. You went through entrenchment ratio, through sinuosity, so you kind of know probably at least what that channel type, or that broad channel type is. So to further refine it, what we're going to do next is we're going to take a dive into slope. And that water surface slope is a field measurement from the top of a riffle to the top of another riffle, at least 20 bank full widths upstream or downstream. This is considered the average slope. And so A and B channel types have the steepest slope. E, C, D, and DA streams have the lowest slope. This is another measure that Heather's going to cover in her survey methods presentation later on. The last piece, I know this is a lot to go through and I'm going through it pretty quickly, so I apologize for that. The last piece though is related to the bed material. Everybody loves to take these measurements in the field, since nothing says Alaska like sticking your arm deep in ice cold water about 100 times to complete a pebble count survey. But like sinuosity and slope, Heather's going to cover this in the methods presentation, the survey methods presentation later. But the key takeaway here is that you need to know the diameter of the median particle size, or D50, of the bed. This just means that 50% of the bed material is smaller, 50% is larger. And so depending on the D50, you'll be able to classify your channel. For example, if your measurement puts you in an A channel type and your D50 was bedrock, then you're gonna be an A1. If it's a cobbled D50, you're gonna have an A3 type channel type. If it's sand, it'll be an A5, for example, and so on. So that's kind of a breakdown of channel classification, again, pretty quick. Now that we've covered a little
Matt,
bit. Yeah.
So we're coming up on 2:30.
Yeah.
And you've got a bit left here. I personally want to hear the rest of your talk. So
yeah, I have 10 slides and I think the rest of it's pretty quick.
Okay, but I just go ahead and keep going. If folks need to leave at 2:30, we understand, and we will be recording this. But yeah, please continue.
Thanks, and sorry for going long. Now that we've covered a little bit about channel classification, this is a really good time to visualize the position of channel types and the associated fluvial processes across the landscape. Here we see A, little a plus, and A channel types, how they would be arranged most likely in mountain headwater or source zones. B channel types would be expected in the mountain settings where slopes begin to moderate, and those are often called transfer or transport zones. And then you get into C and D and E channel types, and those would be most common in those low gradient valleys considered depositional or response zones. So the next part of the presentation I'm going to touch on briefly is just channel evolution. So once you've classified your reach, it's also important to consider what state your project reach is in, given the mix of channel types that might be present and the surrounding valley type. Dave Rosgen outlines 20 channel succession scenarios based on actual field measurements. And for the sake of time, I'm only going to focus on this first 6. But you can see the different channel types and how they might progress from a stable state through an unstable state back to a stable configuration. So that kind of middle section of each of these sequences is considered kind of that evolution through unstable states where the stream is responding to some disequilibrium. And so understanding if your project reach is at risk of adjustment is an important consideration here. And so I'm going to show you an example using scenario 6. A common thing that I often encounter, typically with placer mining, is a situation where you've had a head cut or a base lowering of the stream channel. This site was located in a confined alluvial valley with a stable channel type of a B channel. This is a view of the head cut looking upstream. So you can see the waterfall. That waterfall is a head cut and it is migrating upstream. And upstream you have a stable B channel type and with a well-connected flood prone bench. Downstream of that, you have an incised G channel type. This head cut resulted from poor stream reclamation practices. And this is looking downstream, so you can see it's in size significantly disconnected from its floodplain. Over time, this incised channel will laterally erode, create a new floodplain consistent with that succession scenario 6. It's an important consideration if you have a head cut downstream of your project, because eventually it'll be on the doorstep of your structure. So why does it matter? We all know that culverts can result in excessive scour from increased flow concentration. This increased scour can result in channel degradation and perch culverts locally. But it's also important to note that perch culverts can be a result of head cut migration upstream. Reach level incision, or the progression of incision into your project reach, can be identified during this initial assessment work and help you avoid potential future problems. All right, so this is the home run stretch of my presentation, regional curves. For those of you that aren't familiar with regional curves, or regional hydraulic geometry curves, these are log plots comparing bankful channel characteristics like width, average depth, cross-sectional area to drainage area. Here we see 3 different curves, 3 plots that speak to the northern portion of interior Alaska. These are curves derived from BLM data. And so what you see as drainage, and this is consistent across all regional curves, as drainage area increases, the bankful area, width, and depth also increase. But the important thing is regionally, the height of that, the vertical height of that line and the slope of that line are different. Changes in the coefficient shift that line vertically, while the exponent of that power equation that's listed here describes the slope of the line. The R² value shows the correlation between the drainage area and those bankful measurements. And in this example, we see that across these 3 curves, we have an R² value of 0.82 to 0.91, which indicates a pretty high correlation between the drainage area and these bankful measures. And so I'll show an illustration of some curves from the lower 48 too, to give you guys some context. But this is the curve for the northern portion of interior Alaska. And this is a map showing kind of where these curves would be applied. So during this presentation, I've talked a lot about understanding your fluvial landscape, why it's important for planning fish passage projects. But in some cases, the site you may be working in might be disturbed, making the identification of bankful features difficult or very questionable. Or you might be just seeking to validate the bankful indicators that you use during your reach assessment and cross-sectional data collection. Regional curves can provide another series of data to help you understand your project reach and validate what you're measuring or what you're looking at. Over the last 10 years, the BLM has been working to develop watershed specific as well as regional curves to assist with stream reclamation planning. We're in the process of finalizing a stream design guide for placer mine streams in interior, and the appendix of that report, which we hope to get out here in the next few months, is going to include a list of watershed specific curves as well as these regional composite curves for northern and southern portions of interior. We're also in the process of developing a regional curve for South Central Alaska, but it's a little bit further behind. Taking a closer look here for interior Alaska projects, kind of north of the Yukon, just a rough line boundary. These equations can be used to help validate those bankful determinations. So if you're north of the Yukon, this is a good curve to potentially look at to validate your cross-sectional area, width, and depth, primarily your bankful area, cross-sectional area. For projects south of the Yukon, here's your equation. It's only slightly different. There's not a huge difference between the northern and southern. The coefficients is slightly larger on the northern curve. If you're curious how Alaska curves look against lower 48, this plot shows that very thing. And so it's just important to note that precipitation, runoff behavior, geology, groundwater interactions, those things all help shape that bankful channel dimension and the slope of the line. You see here that our Alaska curves have a similar slope and coefficient as the Michigan power equation. It's very interesting, right? In general, regions with greater precipitation have larger y-intercepts or coefficients and versus the drier regions. And I think this shows it pretty clearly. So just wrapping up my last couple slides here. So why should you care about regional curves? I've talked a little bit about validating your bankful indicators. But you might have all kinds of great indicators. You might have a long gauge history for a project or both. You have all these resources. This is another tool to help validate that characterization of your reach. Fish passage projects are expensive. We all know that. So it's important to minimize risks. If you size the channel too small, you increase energy, resulting in scour and other problems. Likewise, if you size the channel too large, you end up with problems like you see here with aggradation. In this case, the culvert batteries were too big. They span an area much greater than bank full. As a result, we had poor sediment transport and aggradation. In general, we want to support bank full discharge within the channel and ensure that anything more than bank full discharge is on the floodplain or flood prone bench. Hopefully with expanded coverage of our regional curves, you'll be able to have another tool in the toolbox for fish passage and stream restoration planning. And like I said, we're close to getting our interior curves out, and then maybe the next year or two, we'll be able to get the south central curve out. So that's it for me. Sorry, I ran over a few minutes. These are some of the references if you're interested in digging a little deeper into channel classification, valley typing, etc. If folks have questions, my contact information's here, and feel free to reach out.